The Cambrian period began around 541 million years ago, marking one of the most profound and enigmatic turning points in the entire 4.6 billion year history of our planet. For the preceding 3 billion years, life on Earth had been almost exclusively microbial, vast mats of cyanobacteria and other single-celled organisms building layered stromatolites in shallow waters, drifting plankton clouds, simple filaments, and microscopic spheres, quietly oxygenating the atmosphere, one slow breath at a time. Then, in the late Ediacaran, around 575 to 541 million years ago, the first multicellular forms appeared, soft, quilted, frond-like organisms such as Dickinsonia, Sprigina, Charnia, gliding or anchored to the seafloor, absorbing nutrients directly through their surfaces, lacking mouths, eyes, limbs, or any hard parts, more like living doilies or flattened bags than true animals. They lived in a world of low oxygen, gentle currents, and dim sunlight, their fossils preserved as faint impressions in fine mud, hinting at something new, but still quiet, still slow, still simple. Then, almost suddenly, in geological terms, within perhaps 20 to 25 million years, the Cambrian Explosion unfolded. Between approximately 541 and 520 million years ago, animal life diversified with breathtaking rapidity, producing nearly all the major body plans, phyla, that exist today, in a burst that paleontologists still study and debate. Was it triggered by a rise in atmospheric and oceanic oxygen levels, crossing a critical threshold that allowed larger bodies and more active metabolisms? Did the evolution of predation itself act as a catalyst? Arms races driving armor, eyes, mobility? Perhaps changing ocean chemistry made calcium carbonate and other minerals easier to precipitate into shells and skeletons. Or was it ecological opportunity, newly opened niches after the Ediacaran forms faded, allowing experimentation without competition? Whatever the precise spark, the result was a quiet revolution, not announced with thunder, but with the soft rustle of new limbs, the first faint click of chitin, the slow opening of compound eyes beneath a younger, brighter sun. These warm, shallow Cambrian seas spread across continental shelves and tropical lagoons, sunlight piercing the surface in pale golden shafts, illuminating a seafloor of fine mud and microbial films, gentle currents carrying microscopic plankton, the water itself holding dissolved minerals and the first hints of complex organic molecules. Here, in depths no greater than a few dozen meters, life began to explore forms and functions it had never attempted before. No dominant predators yet commanded the scene, no thunderous herds crossed the bottom, only the subtle hum of water moving over sediment, the occasional bubble rising from a microbial mat, the faint settling of tiny particles through the water column. Strange, wondrous, and often fleeting forms began to appear. Trilobites with their three-lobed bodies and calcite shells, Anomalocaris sweeping through the water with grasping appendages, Opabinia probing the mud with a single, flexible proboscis, Wiwaxia crawling with scale-like armor, and countless others, soft-bodied, experimental, many destined to vanish as quickly as they arrived, yet together establishing the quiet foundation for every animal body plan that would ever follow, including our own distant ancestors. This ancient world, still tentative, still discovering, was a place where the rules of life were being written one small innovation at a time. in silence, in warmth, under a sun that feels both familiar and impossibly young, where the first true animals opened their eyes, flexed their limbs, and began the long, patient journey toward complexity. Imagine a shallow seafloor 550 million years ago, in the late Ediacaran period, a vast, gently undulating expanse of fine silt and mud, bathed in diffuse, pale sunlight that filters down through warm, slightly turbid water. The seafloor is almost entirely covered by thick, living microbial mats, thin layers of cyanobacteria and other microorganisms, forming a dark green, almost velvety carpet that ripples faintly with each slow pulse of current. Rising from this carpet here and there are stromatolites, low, rounded domes and columns, layered structures built up over generations by the same microbes trapping sediment, particle by particle. Some no larger than a dinner plate, others rising a metre or more like ancient stone mushrooms, their surfaces textured with faint concentric ridges, glistening with a thin film of mucus-like slime that helps bind everything together. Scattered across and within these mats are the first truly multicellular organisms, soft, enigmatic forms that bear little resemblance to anything alive today. Dickinsonia, the most abundant and familiar, appears as flat, quilted discs or elongated ovals, ranging from a few centimetres to over a metre long, their surfaces divided into a pattern of raised, quilt-like segments radiating from a central line, like a soft, fleshy leaf spring pressed into the mud. They rest directly on the sediment or glide imperceptibly slowly across it, propelled by unknown means, perhaps waves of muscular contraction, perhaps simple, passive drifting, absorbing dissolved organic nutrients and perhaps symbiotic microbes directly through their skin-like surface. No mouth, no gut, no anus, no specialized feeding structures of any kind, just quiet, passive existence, their bodies leaving faint, negative relief impressions in the fine sediment as they move or decay. Nearby, other frond-like forms sway gently in the current. Charnia, tall, leaf-shaped fronds anchored to the bottom by a disc-like holdfast, their branches alternating in a fractal pattern, flexing softly back and forth like underwater ferns, filtering tiny particles or hosting symbiotic algae. Sprigina, segmented, worm-like creatures, crawl or glide with a slow, sinuous motion, their bodies covered in a thin, flexible cuticle, leaving meandering trails behind them. Rangeomorphs, bush-like or sea pen-like fronds, stand upright, their surfaces intricately branched in a self-similar pattern, capturing nutrients from the water column without any apparent movement beyond passive swaying. All of these organisms are entirely soft-bodied, composed of tissues that leave only the faintest impressions when buried. No hard shells, no teeth, no claws, no mineralized skeletons, nothing that could fossilize easily. Only the delicate molds and casts preserved in fine silt when storm events or gentle burial sealed them into the sediment. The water itself is warm, perhaps 25 to 30 degrees Celsius in these shallow tropical or subtropical settings. Oxygen levels low by modern standards, barely enough to support larger multicellular life. Sunlight dimmed as it passes through a hazy atmosphere richer in carbon dioxide and methane, casting everything in soft, diffused light, with few sharp shadows. There are no predators in the modern sense, no jaws snapping shut, no claws slashing, no pursuit across the bottom, only the slow drift of nutrients The patient growth of microbial films, the occasional release of gas bubbles from decomposing mats, the faint settling of fine particles through the water column. Life here is simple, slow, patient, existing in near equilibrium with its environment, waiting, though no one at the time could have known it, for a spark that would ignite the most dramatic diversification in evolutionary history. These Ediacaran organisms, preserved in extraordinary detail at sites like Mistaken Point in Newfoundland, the Ediacara Hills in South Australia, and the White Sea region of Russia, represent the last chapter of a world dominated by softness and simplicity, a prelude written in mud before the Cambrian seas began to fill with the first hard parts, the first eyes, the first real movement, and the quiet explosion of animal complexity that would reshape the planet forever. Then, around 541 million years ago, something shifts. A subtle but irreversible threshold is crossed in Earth's long, quiet history. The precise trigger remains one of paleontology's most intriguing open questions, perhaps a gradual rise in atmospheric and oceanic oxygen levels, finally reaching concentrations high enough to support larger bodies, faster metabolisms, and more active lifestyles. Perhaps the opening of new ecological niches, as Ediacaran's soft-bodied forms declined or were outcompeted, left room for experimentation. Perhaps changing ocean chemistry, increased availability of calcium, magnesium, and other ions made it energetically feasible for organisms to precipitate minerals into hard parts for the first time. Or perhaps all of these factors converged. A perfect storm of environmental opportunity and biological potential, allowing life to move beyond its previous limits in a span of just a few tens of millions of years. An eye blink in geologic time, shallow tropical seas, spread across vast continental shelves and island arcs, become the primary stage for this transformation. The water is warm, perhaps 25 to 30 degrees Celsius, clear enough in places for sunlight to penetrate tens of meters, illuminating a seafloor of fine carbonate mud, rippled by gentle currents, dotted with microbial mats and low stromatolites that still dominate much of the bottom landscape. These layered structures, built by cyanobacteria trapping sediment grain by grain, continue to thrive, some forming broad, reef-like platforms, others standing as isolated domes, their surfaces slick with microbial slime, releasing tiny bubbles of oxygen that rise slowly toward the surface. But now, among and upon these ancient microbial foundations, entirely new forms begin to appear. Small, shelled creatures emerge, no larger than a few millimeters to a couple of centimeters, yet revolutionary in their implications. Tiny hyoliths with conical, calcareous tubes, open at one end, capped by a small lid-like operculum, protrude from the sediment, filter feeding on drifting plankton, their shells thin but rigid, the earliest widespread evidence of biomineralization. Nearby, early brachiopods, small bivalve-like organisms, anchor themselves to the seafloor or to stromatolites, their two valves hinged together, opening just enough to extend a delicate lopophore, a feathery feeding structure that traps microscopic food particles from the gentle currents, their shells composed of calcite or a chitin phosphate mix, offering the first true armor against the emerging possibility of predation. The water hums softly with life, microscopic plankton drifting in slow, lazy swarms, coccolithophores and other single-celled algae shedding tiny carbonate plates that settle like fine snow. Sunlight dappling the seafloor in shifting patterns, sediment stirring in slow eddies around each new, hard structure, the faint patter of falling particles, the occasional soft click as one shell brushes against another. No roaring, no violence, no sudden frenzy, only the first whispers of hard parts. Calcite shells glinting in the light, chitin exoskeletons beginning to appear in even smaller forms, the quiet invention of protection, of structural support, of limited but real movement, and, inevitably, of predation. These earliest armoured animals, still tiny, still tentative, represent the opening notes of a symphony that would soon crescendo. They crawl, burrow, attach, filter, each innovation small, each survival advantage modest, yet collectively laying the groundwork for jaws, limbs, eyes, and all the complexity that would follow. In these warm, shallow waters, under a sun that shines brighter and longer than it had for billions of years, life is no longer merely enduring, it is beginning to explore, to compete, to diversify in ways that would reshape the oceans and ultimately the entire planet forever. Among the earliest and most enduring icons of the Cambrian Explosion, Trilobites emerge as true pioneers of complex animal life, segmented, armoured, and equipped with the first compound eyes known in the fossil record. These small arthropods, often no larger than a few centimetres, represent one of the most successful and diverse animal groups ever to appear, eventually producing over 22,000 described species across more than 270 million years. Yet their story begins quietly, in the earliest Cambrian strata, around 521 to 514 million years ago. Picture one now, a small Olanellus, perhaps 3 inches long, gliding slowly across the soft, fine-grained mud of a shallow Cambrian shelf. Its body is distinctly three-lobed, a wide central axial lobe flanked by 2 pleural lobes, each pleura extended outward in a series of flat, feather-like segments that give the animal its name, Trilobite, meaning three-lobed. The exoskeleton is thin but rigid, composed of calcite, a mineral that preserves beautifully, its surface smooth or faintly granulose, coloured perhaps in muted olive or grey tones that blend with the sediment. At the front, the cephalon is broad and semicircular, bearing a pair of large, crescent-shaped compound eyes, holocrole in structure, packed with hundreds of tiny hexagonal lenses, glinting faintly in the dappled sunlight, the first true eyes on Earth, capable of detecting light, shadow, and perhaps vague movement or contrast. A revolutionary adaptation that would forever change how animals interact with their world. Olanellus moves with a deliberate, almost stately grace, its many legs, biramous, with a walking branch and a gill branch, propelling it forward in a smooth, undulating crawl across the seafloor, leaving faint trackways behind, the trace fossil cruziana, paired grooves that paleontologists still find in Cambrian rocks worldwide. It pauses to feed, pleurae fanning slightly, head lowered, using its limbs to sweep microbial mats and fine, organic particles toward a ventral mouth, filtering, scraping, ingesting the nutrient-rich film that coats the bottom. When threatened, or simply as part of its growth cycle, it burrows shallowly, curling into a defensive ball, or swims weakly upward in short bursts, lobes flapping, before settling again, periodically, Like all arthropods, it molts, shedding its rigid exoskeleton in one piece, the cephalon splitting along the facial sutures, the thorax and pygidium following, leaving behind a delicate, empty husk that drifts briefly before settling into the mud, a perfect imprint of the living animal, preserved when buried quickly by the next influx of sediment. These molted shells accumulate layer upon layer, contributing to the slow hardening of the seafloor, the first hints of biogenic carbonate sediment, a quiet revolution in how the planet recycles its own materials. More trilobite forms soon arrive, larger, more elaborate, paradoxides, sometimes reaching 45 centimeters or more, its cephalon spiny and elongated, thorax composed of numerous segments, pleurae extended into long, protective spines, allowing it to swim more effectively in schools or roll into a tight defensive sphere when danger approaches. Their calcite shells, thicker, more ornate, accumulate in dense layers, forming the first widespread bioclastic limestones, the seafloor slowly transitioning from soft mud to a firmer, shell-paved substrate, providing new surfaces for attachment, new niches for filter feeders, new opportunities for the quiet diversification that defines the Cambrian. These armoured pioneers, still small in the grand scheme, still tentative, are already reshaping the oceans, introducing concepts of protection, vision, mobility, and molting, laying the silent groundwork for every subsequent chapter in the history of animal life. In these same warm, shallow Cambrian seas, stranger forms begin to appear, organisms so unusual that when they were first discovered in the early 20th century, paleontologists could scarcely believe they were real animals at all. Anomalocaris canadensis, the so-called anomalous shrimp, emerges as one of the most imposing and revolutionary creatures of the period, reaching lengths of up to 3 feet in the largest specimens, its body elongated and flexible, divided into a series of wide, lateral swimming lobes that undulate rhythmically, propelling it forward with a slow, sinuous motion through the water column. These lobes, fringed with delicate setae, function both as gills and as the primary means of locomotion, giving the animal an almost ethereal, wave-like grace as it glides. At the front, a pair of large, segmented, grasping appendages extend forward, jointed, flexible, each ending in a cluster of sharp spines, capable of curling inward like a pair of powerful pincers, sweeping through the water, capturing soft-bodied prey with startling precision. The head is broad, armed with a circular, toothy mouth ringed by 32 overlapping plates, each armed with small, conical teeth, arranged in a radial pattern that could constrict and crush, or slice and tear, depending on the motion, a feeding apparatus unlike anything seen before, the first true jaw-like structure in the fossil record. Above the mouth, 2 large, compound eyes sit on short stalks, swivelling independently, each eye composed of thousands of tiny lenses, providing a wide field of vision and perhaps the ability to detect motion, contrast, and even polarized light, making Anomalocaris the first apex predator, a silent, efficient hunter that patrolled the open water and the upper layers of the seafloor. Imagine one now, gliding slowly through the sun-dappled water, lobes rippling in gentle waves, the faint current tugging at the fine setae along its edges, eyes swivelling on their stalks, scanning the drifting plankton and the soft-bodied creatures below. It detects a cluster of small, frond-like Ediacaran survivors or early Cambrian worms. Appendages extend, curl, grasp, pulling the prey toward the mouth ring, the radial teeth closing with a quiet, mechanical precision, crushing, swallowing, the entire process taking only seconds. No sound, no thrashing, just the soft displacement of water, the faint settling of disturbed sediment, the predator moving on, leaving little trace beyond a momentary cloud of particles nearby, drifting with an almost dreamlike slowness. Another extraordinary form appears, Opabinia regalis, no more than 5 to 7 centimeters long, yet possessing a body plan so bizarre it was initially met with laughter when first reconstructed in the 1970s. Its head bears 5 large, compound eyes on flexible stalks, arranged in a semicircle, providing panoramic vision, while from the front extends a long, flexible proboscis, segmented, ending in a claw-like grasping structure, capable of reaching forward and seizing small particles or prey, then bending back to deliver them to a mouth located underneath, near the base of the head, a feeding method unique in the animal kingdom. The trunk is segmented, soft, with lateral lobes similar to those of Anomalocaris, but smaller, more delicate, aiding in slow swimming and respiration, while the tail fans out into a series of flat, overlapping plates, forming a broad, propulsive fin that undulates gently, propelling Opabinia forward or allowing it to hover above the sediment, probing the mud for organic debris or tiny organisms. There is no sound, only the gentle undulation of its lobes, the faint stirring of water around the proboscis as it extends, grasps, retracts, the soft settling of disturbed silt, the occasional flick of the tail fan, an alien beauty drifting in the current, neither predator in the aggressive sense nor passive filter feeder, but something in between, a quiet experimenter in form and function, one of countless strange trials in a world where evolution was still writing its first drafts, testing every possibility, discarding most, yet keeping the innovations that would echo through hundreds of millions of years to come. In places like the Burgess Shale in British Columbia, Canada, and the equally remarkable Chengjiang Biota in Yunnan Province, China. These early Cambrian animals are preserved in extraordinary detail, far beyond mere skeletal remains. The conditions were exceptional: rapid burial in fine mudslides, anoxic bottom waters that slowed decay, and mineral-rich sediments that replicated soft tissues with almost photographic clarity, allowing paleontologists to see not just hard parts but muscles, gills, digestive tracts, eyes, even the delicate appendages and nervous systems of creatures that lived over 500 million years ago. These sites, along with others such as Sirius Passet in Greenland and Emu Bay in Australia, offer a rare window into a world of quiet experimentation, where evolution was testing every conceivable body plan, discarding most, refining a few, in a burst of creativity that would define animal life for the next 500 million years. Among the strangest and most evocative of these forms is Hallucigenia sparsa, a small worm-like creature no more than 3 centimeters long, its body armored with pairs of tall, flexible spines rising along the back, and 7 pairs of slender, tentacle-like legs beneath, each tipped with tiny claws. For decades after its discovery, it was reconstructed upside down. The spines thought to be legs, the legs interpreted as tentacles, until better specimens revealed the true orientation, a bizarre, spiny crawler that may have grazed microbial mats or probed the sediment for organic particles, its spines perhaps serving as defense, display, or even sensory structures. An animal so alien it seems almost hallucinatory, hence its name. Nearby drifts Wiwaxia corrugata, a flattened, oval-shaped creature, up to 4 centimeters long, its back covered in dozens of overlapping, scale-like sclerites, each one a tiny, overlapping plate of chitin, giving the animal a shimmering, almost armored appearance, with longer, thorn-like spines projecting along the midline, possibly for protection against early predators. It crawled slowly across the seafloor, mouthparts scraping or sucking at organic films, leaving behind faint, grazing traces. A quiet, armoured browser in a world still learning what armour could mean. Marrella splendens, delicate and graceful, glides through the water column, its body no more than 2 centimeters, with a shield-like cephalon, long, sweeping antennae, and dozens of biramous appendages, each one feathery, used for both swimming and feeding, propelling it in slow, rhythmic pulses, a beautiful, almost ethereal swimmer, one of the most abundant animals in the Burgess Shale, its fossils numbering in the tens of thousands, showing just how successful these early experiments could be. And then, perhaps the most significant of all, Pikaia gracilens, a slender, eel-like chordate, only a few centimeters long, with a notochord running the length of its body, the flexible, supportive rod that would one day become the backbone of vertebrates, including our own distant lineage. It swims with gentle, lateral undulations, filter feeding through a pharynx lined with gill slits, a simple, unassuming creature, yet carrying within its anatomy the quiet blueprint for fish, amphibians, reptiles, birds, mammals, and ultimately us. Life in these Cambrian seas diversifies, not with noise, not with sudden catastrophe, but with slow, patient invention, new body plans appearing, bilateral symmetry becoming standard, segmentation, appendages, sensory organs, digestive tubes, protective coverings, modes of locomotion from crawling to swimming, feeding strategies from filter feeding to active predation, all emerging in a relatively brief window, in warm, shallow seas bathed in sunlight that feels younger, brighter, full of untapped possibility. These strange, wondrous animals, many destined to leave no descendants, others the ancestors of entire phyla, together set the stage for everything that followed, from the trilobites that would dominate Paleozoic oceans to the first fish, amphibians, reptiles, dinosaurs, mammals, to us. Listening now, carried on the same deep currents of time that began their journey here, in the quiet explosion of life beneath an ancient sun.